My guest today is Monika Schleier-Smith. Monika is an associate professor in the physics department here at Stanford. Her work is in the field of quantum mechanics, which is at the heart of technologies like MRI machines, laser, fiber optics, GPA satellites, and computers. Monika is an experimental physicist. She has devised and implemented experiments that allow her to isolate and manipulate physical phenomena that were not previously accessible in experiments. Her research focuses on advancing the optical control of interactions among laser-cooled atoms with an eye towards applications in quantum simulation, metrology, and computation. Monika received her bachelor degree from Harvard and her PhD from MIT. She is a 2020 MacArthur Fellow for her work advancing our understanding of how many particle quantum systems behave and connecting phenomena observed in the laboratory to a wide range of other areas of physics. Now, Monika has also received the Sloan Research Fellowship and the NSF Career Award. She's a fellow of the American Physical Society and the recipient of the Presidential Early Career Award for Scientists and Engineers, as well as the Rabi Prize in Atomic, Molecular, and Optical Physics. So welcome, Monika, and thank you very much for being here.
Thank you.
So let me start with asking you just the simple question of how did you become interested in quantum mechanics?
Yeah, so I think my interest in quantum mechanics probably dates back to high school. And in particular, I had a really great high school chemistry teacher who, when talking about electrons in molecules, he would paint this picture that an electron is not just at a point, but it's sort of smeared out like peanut butter, he would say. And this was his way of describing sort of the fundamental quantum uncertainty in where a particle is and the fact that you sort of can't know where a thing is and how fast it's moving at the same time. Those ideas were fascinating to me, and I wanted to sort of not just have the hand-waving picture, but really understand the math behind it and get to play with it in the lab, and that's something I get to do today.
Nice. So I know nothing about quantum mechanics. So what does the field try to understand? And maybe you can explain to us the concept of entanglement, which is at the core of some of your work.
Yeah, right. And so quantum mechanics governs particularly the behavior of matter at very small scales, atoms, particles, particles of light, photons. This is where quantum mechanics starts to matter. It's something, I mentioned quantum uncertainty. That's not something you notice in your day-to-day life. You can know that your car is parked in your garage, you know where it is, you know that it's at zero velocity, but quantum mechanics says you shouldn't be able to know both of those things at the same time. And so these effects start to become noticeable at microscopic scales. So something that's really fundamental about quantum mechanics is that really the laws are probabilistic. These are laws that sort of, there's an inherent uncertainty, and that connects to this idea that you mentioned of what's called entanglement. So entanglement is the notion that actually there can be sort of correlations and information that's encoded not just in individual particles, but in correlations between them. So as an example, in your classical computer, information is stored in individual bits that could be a 0 or a 1. And the quantum version of that is something that we call a qubit, which actually can be sort of a 0 and a 1 at the same time. It's fundamentally unknown which one it is until you perform a measurement, and then it kind of has to decide. And I often kind of think of this notion of what's called quantum superposition, this qubit that's sort of in two states at once, as a little bit like a coin that's hanging in midair and it hasn't decided whether it's going to land heads or tails. So the funny thing in quantum mechanics is we could have a situation where Ran and I are each tossing coins. And this is my analogy for measuring the state of a quantum bit. So I'm tossing my coin, and you're tossing your coin, and every time mine lands heads, his lands heads, and every time mine lands tails, his lands tails. That's weird. That would never happen, right, with you and your friend tossing coins. But that can happen when we measure the states of quantum particles. And that is what's known as entanglement. There's some information that I don't have. When I toss my coin, the outcome looks flat random. Ran doesn't have that information either, but when we compare notes, there's actually some structure and some information there. And that is a fascinating phenomenon that has lots of implications that we can talk more about.
Right,
yeah.
so it's kind of amazing. I mean, when I think about, classical physics is simple, or let's say simple to at least visualize. I roll the ball, and because there is friction, it will eventually stop. I can visualize it with my own eyes. But entanglement is a little bit more difficult to understand. I think even Einstein couldn't make sense of this, and he called it spooky action at a distance. And so I was trying to think about like examples for my own life of what it is, and the only example I could think of is my marriage. So no matter how far apart my wife and I are, our thoughts and behaviors are very strongly correlated, and this in a way that is appears magical at sometimes. And is it because to begin with, we were such a good match to each other? Is it because we know each other so well? Is it because we shared so much information in the past? So, what explains the magic of entanglement in the quantum world?
Right. Yeah, and I think it feels a bit magical, but it's not complete magic, right? And so, for example, one of the questions people will ask is, I talked about these two coins that are entangled, and it could be me with my quantum particle here at Stanford and somebody who's in Paris with another quantum particle, and even over long distances, in principle, these types of correlations can be there. And so people sometimes ask the question, well, does that mean you can communicate faster than light or something? And the answer is no. The answer is you still need some way for these correlations, this entanglement, to develop. And so in the analogy of you and your wife, it's probably to some extent those interactions over sort of years that build up this sort of common way of thinking, right? You had to interact over time in order to build up this entanglement. And similarly, two particles need some way of interacting and exchanging information or becoming correlated in order to build up this phenomenon of entanglement. It could be that I send a photon from one place to another, and that photon carries information that allows this process of entanglement to take place.
Yep. And one of your big contributions is that you don't just theorize about entanglement, but you're able to show in your lab experiments that actually show this entanglement. So how do you do that?
Yeah, that's right. So in my lab, the sort of toolbox that we work with are atoms that we control with laser light. So it turns out that you can actually use laser light to cool atoms down very close to absolute zero temperature. That might sound counterintuitive because a laser is a source of energy. So if you're curious, you can ask later how that works. But the point is that this is a way of having a very well-controlled quantum system where I have atoms that I can essentially bring to a standstill. I can essentially pin them in place using focused laser beams. And this is actually a starting point for having each atom act sort of like one of these quantum bits. I can store information in the atoms. And I can use light to carry information between the atoms that can build up this entanglement. And I can also use light to take pictures of the system. So all of this is happening somewhere in an ultra-high vacuum chamber where there's just the atoms we want and nothing else. Other than that, it's empty space. We have light to manipulate them. We have light that we shine in, and we can actually take pictures on the camera that tell us is an atom in the one state or the zero state, if I think of it as this quantum bit.
So if you invited me to your lab, for example, if I come today, what will I see there?
Yeah. So first of all, you would walk in and you would see a lot of equipment. You would see several tables, each of which has lasers on it, lots of mirrors to direct the laser beams in the right places. The light gets sent into optical fibers that carry it to that vacuum chamber where the science actually happens. And if you sort of peer through the window of that vacuum chamber, you might actually see this cloud of cold atoms collecting. Depending, the atoms in my lab, they emit light at a wavelength that your eye can't quite see. But if you look with an infrared viewer, you can actually see a little glowing ball of atoms collecting at a temperature that's some millionths of a degree above absolute zero. But you'd also see a lot of cables running around, computers to control everything, lots of fun toys.
Yep.
So, yeah.
Can you recall like a particular aha moment that happened, that you saw something in the lab that you kind of knew right there that this was a new discovery that no one has seen before?
That's an interesting question. I would say actually a lot of the work that I've done in this field is something where I might call it quantum engineering. So we have an idea of where we're maybe trying to go. And we know that in principle, there's maybe a way to make a certain entangled state that has some useful property. Maybe it allows you to build a better atomic clock, is an area that I worked in my PhD. And the hard part is actually figuring out kind of how exactly do you get there, but also sort of making the experiment good enough to manipulate these fragile systems in the lab. And so I would say, in some cases, the aha moment, so day to day, it's often that you're troubleshooting. Why did it not do what I thought? So this is a field where you have to love actually just seeing something that didn't work the way you expected and trying to figure out why, and that whole problem-solving process. So sometimes the aha moment is fixing the last problem and then seeing the result that one was aiming for, or sometimes the aha moment is something where maybe coming up with a new idea for how to engineer the system that we want. And I think one moment in that spirit that I can recall is actually as a graduate student. There was a day when some of the equipment in the lab was broken, and there were two of us working on the project. So my peer was sort of in the lab fixing the equipment, and I had one day to sit and sort of reread a paper that I think my advisor had given me probably on my first day of graduate school, and it was on a pile on my desk. And I sat and reread it and realized that the paper was proposing to make a certain type of entangled state, and it said if you had this form of interactions, you could make this state, and it could improve your precision measurements, but we don't know how to make this form of interactions. And I read that paper, and I realized, oh, but that sounds like something that we were just measuring in the lab. And sort of putting those two things together actually allowed us to reach this goal of kind of improving an atomic clock by entanglement. And so that was very satisfying.
Let's talk a little bit about some potential applications of entanglement and quantum mechanics. You mentioned in your PhD you worked on mechanical clocks. At the time, I think you designed like a clock that was much more precise than standard clocks. But can you tell us about some applications of this idea?
Yeah. So broadly speaking, there's a number of different directions in which entanglement can be useful. So I mentioned earlier this idea of entanglement over long distances. And it turns out that can be a resource for fundamentally secure communications. So if you want to convey information in a way that is completely eavesdropper-proof, there are ways in which quantum mechanics can give you really a kind of let the laws of physics prevent somebody from eavesdropping on that communication. So that's kind of one application that benefits from entanglement across long distances. But another direction of application is that you maybe sort of hear about if you kind of read the news is computation. And that's one where really the fundamental idea, I would say, is that as soon as you have to keep track of not just the states of individual bits, but the correlations between these qubits, the description of a system of even just a small number of quantum bits is exponentially complex. So basically, if I want to describe a system of just some tens of quantum bits on a classical computer, it actually wouldn't fit even on the world's largest supercomputer. And that's because I need to keep track not just of is this qubit in the 0 state and is this one in the 1 state, but if this is in 0 and this is in 1, is this third one more likely to be in 0 or 1? And this, you can imagine, this quickly grows very complex. So that gives you some indication. You can't even fit the description of a small number of qubits onto the world's biggest supercomputer. That suggests that maybe there's some computing power that classical computers don't have. And indeed, there's no question that for solving certain problems that are inherently quantum mechanical, that might be chemistry problems that rely on the quantum mechanics of electrons, problems in which materials are superconductors. That is, again, a problem that involves the quantum mechanics of interacting electrons. That's something that classical computers can't just solve from first principles. And one of the visions of having well-controlled quantum systems in the lab is to be able to compute those hard problems. But also totally classical problems like factoring large numbers. In principle, a quantum computer can do better, and much of the challenge is in getting good enough control over the systems that we build to be able to actually realize this vision of quantum algorithms. So I talked about secure communications, computation, And then you already touched on another one, which is precision measurements. And there, the picture is kind of, again, there's this fundamental uncertainty in quantum mechanics. Measuring the state of a quantum bit is like a coin toss. Reading out the time on an atomic clock has that same sort of statistical uncertainty. I'm measuring, doing some probabilistic measurements on many atoms. Entanglement can reduce that uncertainty if I have something where, if my coin lands heads, another one is more likely to land tails. I could have a situation where I toss 100 coins, and exactly 50 land heads and exactly 50 land tails every time. That never happens in a classical coin toss. There it would be 50 plus or minus 10. But in quantum mechanics, you can actually use entanglement to reduce statistical uncertainty and make better measurements. And that might be of time. It might be of magnetic fields. It might be of gravity. And it might also be used then to tell us something fundamental about our universe.
That's great. So clearly you have had much success in your career. But would you mind maybe sharing with us a project of yours that failed, or a particular moment of frustration, and what have you learned from this experience?
Sure, yeah. So I want to first push back a little bit on the question, because I don't think it's very useful to think in these terms of success and failure. And the reason I say that is part of the nature of doing science is that we're always kind of operating at the frontier of what's known, right? And so the whole process of science is there's something where the problem is unsolved. And what we do is we try different approaches, and most of them don't work. And every so often something works, right? But in that spirit, I think maybe one example I can give is actually when I actually was first kind of starting up my lab here at Stanford. I knew I wanted to do some experiments where we're manipulating atoms with light. And one of my dreams was to have a setup where I can make something called a Schrodinger's cat state. So what is that? It's like, imagine I have many atoms, could be, let's say 100 atoms, and each of them has two different states it can be in, some ground state and some excited electronic state. And imagine you could have something where either all of the atoms, there's a fundamental uncertainty between all of the atoms being in their low energy state or all of the atoms being in their high energy state. So it's like the system is either alive or dead and nowhere in between. Kind of makes sense? It's this like, until you measure it, you don't know, is the system of many atoms alive or is it dead? And it turns out that's a state with a very large uncertainty in energy. It could be a very high energy state or a very low energy state. And quantum mechanics tells you if you can make states with a very large uncertainty in energy, they let you make better measurements of time. And so, but it turns out it's really hard to make this type of state, because you need to not only control what information you have about the system, but what information you don't have, right? You need to make a state that has this large uncertainty. And part of the trick to that is being able to sort of discretely have these atoms talk to each other and share information without any of that information sort of leaking to an outside observer, because you need to maintain this fundamental uncertainty in the system. So part of that for us, actually, in the lab, it involved making a system where we trap atoms between some mirrors that are very, very reflective, and light can bounce back and forth lots of times and convey information between these atoms without leaking to the outside world. And I had ideas for how we were going to make these mirrors super, super reflective so we could make these big Schrodinger cat states. And it turned out that somewhere in the process of building this, one thing went wrong. The mirror surface degraded due to some weird chemistry. But this thing was in this vacuum chamber. It was hard to, we didn't want to open it up and replace the mirrors and try again. And so, it was a little bit disappointing. We were sort of expecting to be able to do this experiment, but we were stuck with a setup that was a little bit different than what we hoped for. At the end of the day, though, I think what you do in this, or what I do in this situation, is I say, well, what do we have and what can we do with it now that's already interesting? We can do that other thing down the line. And it really forced us, because the setup was a bit different than maybe what other people were working with, to actually kind of take advantage of different tools than we were planning on. So for example, it was hard to characterize this. So it was not going to be possible to make those cat states that we set out to make, but we decided, actually we can use this for a totally different research direction of building toy models of quantum gravity in the lab. And I never would have thought to do that, but I had this system, and I had some chance conversations with colleagues who were interested in quantum gravity, and realized, this thing we built, it won't let me do the thing I originally set out to do with this setup. in its immediate form, but I can do this totally different research direction, and one day we can still come back to the original goal. So,
yep.
Yeah.
And you took the lemons and turned them into lemonade.
Yeah, exactly. And I think I think it's healthy to do that, and I probably do that all the time in some form.
Yep.
Yeah.
Now you teach an intro sem here at Stanford, like an introduction seminar for freshmen and sophomores. So I wanted to ask you, what do you teach in this course, and what if somebody doesn't have much background in physics or in math? Can they still come to your class and enroll?
Yeah, absolutely. So this class basically starts by, we take some sort of high school level math. We maybe assume that you've seen what a vector is. That helps. But we don't require any kind of college level math or physics. And we really start by gaining an intuition for sort of what do we mean by quantum bits. What's a physical way that you can actually have a quantum bit? One way is actually it can be light, photons can be quantum bits. And we really do some hands-on demonstrations of actually what happens when you measure the state of a quantum bit that's in this superposition state. You can actually do some simple hands-on experiments with photons and polarizers to get an intuition for how measurements work in quantum mechanics. But we build from there all the way to understanding some of these applications I talked about, secure communications, how does a quantum search algorithm work? And you really actually get a rigorous understanding for how one gets a speed up for the problem of searching, like searching a database, but on a quantum computer. And go all the way up to sort of also what are some of the hardware platforms that people are building in order to realize this goal of quantum computation.
Yeah. I saw that you are an advisor in Stanford, in a program at Stanford for inspiring the next generation of women in physics. And I wanted to ask you, your views about the topic of women's underrepresentation in physics, and what advice you have for women who are inspired by your talk and want to go into physics.
Sure. Yeah. I think so. I should start by saying this program, it's an amazing program, actually. It's a summer program for high school girls that was really started by Stanford students. And every once in a while, they'll reach out to me for a little bit of advice. But it's totally student-run, and it's awesome. But in terms of kind of general advice, I would say I think one of the main things that as an undergraduate, I didn't even realize that I was one of the few women in my classes. Somehow, I think maybe it's helped me that I don't have a problem with also seeing men as role models whom I can follow. But one thing I started to notice as a graduate student was that there are differences in sort of like typical communication styles between men and women that I had to get. And of course, I don't want to overgeneralize, right? But often it would be the case that if I was talking with sort of my male colleagues, I would sort of try to make an argument by asking a question, and they would be the other way around. They would sort of very confidently state something in order to sort of see whether anybody would disagree, and that could be a way of asking a question, right? And so often there are sort of, I think women sometimes come in with a more timid communication style, and if it's a very male-dominated environment where people are being more assertive, it can really take some time to sort of learn how to communicate and be heard in that environment. And so that's something where I actually was lucky that at MIT, where I was a graduate student, there was a women in physics group that would have free dinner every couple of weeks. So I went there just for the free food. But then I would hear people talking about, some of these kinds of situations that they encountered in their own lab, and then come in prepared to sort of realize, oh, it's not just me. This is just, that's how it is. There are these differences in communication styles. I can get used to this. And I think I was, a couple years ago telling one of my students about these experiences, and she said, "What? You used to be timid in communicating? Like, you're the most assertive person I know," or something. And so I guess one can learn, even in kind of a male-dominated field, to feel very at home. So, yeah.
Now, finally, before I open these two questions from the audience, what advice do you have for young students interested in physics in general?
Yeah, I think one piece of advice I would give is there's certainly a difference between classes where you're given a problem set and to succeed in the class, you just sort of go through and you solve the problems, and probably if they're on the problem set, there is a solution. So that's kind of different from research where you're given something open-ended and the solution might or might not be there, and you have to sort of live with this uncertainty or be willing to redefine the problem. And so one piece of advice I would give is just make sure early on, if you're thinking about going into any area of science, but certainly in physics, get real research experience, be it in the summers or maybe you even have time to take on a small project during the academic year, but get a sense of what it's actually like, not just doing classes, but doing research. If you're not sure whether you like theory or doing something more hands-on, try the hands-on thing, see whether it appeals to you, and get some exposure to sort of what are the open questions that people are trying to address, and not just what is the 200-year-old physics that's taught in the classroom. So yeah.
Professor Schleier-Smith, thank you so much.
Thank you very much for the talk. Hello? Hello? I was wondering, for quantum entanglement, do we know the mechanism in which the two particles communicate? Can you elaborate on that?
Yeah, great. That's a great question. So there are multiple different mechanisms for making these quantum entangled states. And so just to give a couple of really specific examples from my field where our particles are atoms, one way that you can entangle them is, for example, have two atoms that are very close to each other, but you sort of want them. So the important thing is you need interactions, but you need a high degree of control. So something you can do is basically trap each atom at the focus of a laser beam, and so you can kind of pin it in place. And the typical distance you might separate them by is about, let's say, a micron. Why a micron? That's about the level, it's roughly the wavelength of light that one uses, and so that's kind of the smallest length scale on which we have control. And so, but an atom actually is much smaller. An atom is an angstrom scale object, so that's kind of like 4 orders of magnitude smaller. And so normally they sort of don't interact if they're held on a micron apart. But if you now excite one of the electrons using a laser to where it's still bound, but just barely, it's sort of like much further from the nucleus, it's kind of a big fuzzy electron now, and you do that for each of the atoms, then you can actually have strong interactions between them. It's actually the van der Waals interaction. It's that same thing that makes like gecko feet stick to a wall. So that interaction at the atomic scale is a way of actually very controllably introducing entanglement in a way that basically there's a pulse of light that allows the atoms to interact, and after that they're entangled. We also play games where we put the atoms further apart, and even with those tricks, they wouldn't talk to each other, but by sending light in a controlled way so that photons can bounce back and forth between them, we can generate entanglement. And so those are a couple of the mechanisms. But again, there's different physical systems and different ways, to do it. Mm-hmm.
I have a question as well. So when you talk about you excite them with the lasers, you make the electron cloud grow in size. How do some lasers cause that excitement in the electrons, and some lasers cause the atoms to be frozen in place at lower energy?
Yeah, that's a great question. The nice thing about a laser is it has a very well-defined frequency, and that corresponds to basically an atom has different sort of electronic states at different energies, and depending on the frequency to which we tune our laser, first of all, we can sort of talk to different electronic states. So that's one thing. Depending on the laser frequency, that could dictate whether we go to one of these, they're called Rydberg states, these sort of big, fuzzy, high-lying electronic states. But also, we have to play additional tricks if we want to slow the atom down. So there it's not, we don't want to just sort of throw energy into the atom. We have to very controllably actually extract energy from the atom. And there we play some tricks that involve the Doppler shift. So that, this effect where if I'm driving this way and there's a truck coming that way, it sounds higher pitched if it's moving opposite my direction of motion. So similarly, if I have an atom that's flying this way and there's a laser that's pointing in the opposite direction, that will actually effectively shift the frequency of the laser. And so you can play tricks where the laser would be too low in frequency to excite the atom if it if the laser and the atom were kind of moving in the same direction. But if the laser is moving this way, it actually resonantly excites the atom and gives it a push that slows it down. And so you can set up a configuration of laser beams in sort of 3 dimensions that are tuned to just the right frequency that they'll tend to slow the atom down rather than speeding it up. And once the atom is slowed down, it'll actually emit light of a higher energy than what it had absorbed. And so that's why it gets cooled down. So the energy goes into the light field. And that's the trick that we use for laser cooling. Yeah.
What advancements do you think need to be made in quantum computing to make it available to the general public?
Yeah, so that's a great question that has sort of multiple layers on it. So, because one of the questions is even, where exactly will quantum computers help the general public? And I gave some sense that maybe for solving chemistry problems that could be useful for drug discovery, we hope that quantum computers can help. So there's a range of sort of, I would say, algorithmic questions of how exactly should we use quantum computers to speed up the tasks that you care about. But the second one is sort of what advances are needed. And one key one that's a really active area of research is basically how do you do error correction for quantum computers? And so classically, it's a little bit simpler because there's basically one type of error, which is that a bit can get flipped. But quantum mechanically, these qubits, they can be like the 0 state or the 1 state. I kind of think of those as an arrow that points down or up. And then they can be in that sort of like superposition of 0 and 1, somewhere in between. And I actually visualize it as like an arrow that can point anywhere on the sphere. And so it's not really a discrete, you might think, oh, it's no longer a discrete thing that can be 0 or 1. It's not just a bit that can flip. There are lots of like small errors that could happen, small rotations of my qubit. And so quantum error correction, this is a beautiful field, actually. Like the theory of it is beautiful. It's not obvious you can do it. It turns out you can do it. But in order to the sort of experimental tools are really just coming online. So you need reasonably good fidelity, so like small gate errors to begin with. And then on top of that, you need some redundancy where you have more qubits, sort of more physical qubits than the sort of logical qubits that are actually encoding the information. And you need exactly the right form of interaction to be able to correct errors. And so there's lots of progress being done right now in this area, but that's a key thing that's going to be needed is to have enough qubits that are well controlled and have that extra overhead of the additional ones for the redundancy to correct the errors. And so lots of progress, but lots of hard work remaining to be done. Yeah.
Hi. Hello?
Hi.
Two-part question. First of all, have you always known that you wanted to go into research in the academic setting? And also, what qualities do you think have served you best as you have gone down this path as a professor?
Yeah, so I think for the first question, have I always known I wanted to go into research in an academic setting? Actually, that has multiple parts. Did I always know I wanted to go into research at all, right? I think that I think it sort of became clear to me over time that I would enjoy this. And it started with, when I was in college, I was enjoying my math and physics and chemistry classes, and somewhere realized that quantum mechanics was sort of the intersection of those things, and I wanted to understand it better, and a natural way was to go to grad school and start doing experiments where I could play with quantum mechanics, and I was enjoying that. And I think for me, I would say, just as general advice, actually, if sort of at every stage you're kind of doing something that you think is fun, then you'll probably do it well, and then you kind of see where it leads. And so when I was starting graduate school, I thought, well, at least I think I want to spend a few years on this, and maybe I'll want to go into teaching, maybe I'll want to go into research. I had a vague sense that there are different settings where you can do research. It could be, in academia. It could be in a national lab. And I don't think I had a clear sense of where I would end up. But I found myself enjoying the academic setting, enjoying sort of the variety of tasks that come. As a graduate student, you're very focused on kind of maybe running one particular experiment. But then as a postdoc, I started kind of having a team of people that I was kind of starting to mentor, and I enjoyed that aspect of it. And so, yeah, I think it was kind of a natural thing that happened over time where I just kept doing what I liked doing, and that's where it led me. There was a second part of the question, which I forgot. Oh, qualities, yeah. I think one thing is kind of just general optimism, because again, like I mentioned earlier on, that at least in experimental physics, a lot of what we do is problem solving and understanding why things don't work. And so enjoying that and sort of having the optimism that we're going to solve all the problems and get to the exciting goal at the end, I think that's super important, and that empowers you to kind of have a big vision and be comfortable also with the uncertainty and exactly how you're going to get there. So.
Hi. Once these qubits become entangled, do we have a knowledge for the maximum distance that qubits can actually be entangled? And is there a maximum number of qubits, not just two, but how many can be entangled at the same time?
So, in terms of the distance, there's no fundamental limit. Again, you need information to pass between them to generate the entanglement. So then, it takes time to have entanglement form over longer distances. But, the challenge is always, both in the distance and the number of qubits, the challenge is what's called decoherence. So basically, in order to have entanglement, you need this fundamental uncertainty in, for example, is the energy in this atom or in that atom, right? You need some kind of fundamental uncertainty, and that means that if you need to be very careful about not having a situation where some observer could, even in principle, know that information. And so the challenge, both in terms of having entanglement across long distances and having it across many particles, is that it becomes easier and easier for just a little bit of information to leak away in a way that could destroy the entanglement. I talked earlier about this concept of a Schrodinger cat type of a state, where I know that either all of my atoms are in their ground state or all of them are in a highly excited state, but I have no idea which of those two things it is. And the more atoms I try to do that with, the bigger the chance that accidentally a photon will bounce off one of those atoms and tell me something about which of its states it's in, and that whole fragile superposition of kind of alive and dead will collapse, and I'll just be left with a cat that's dead, right? And so that's what you want to avoid, and that gets harder and harder, basically, the more particles you're dealing with. And so a lot of, I would say, the exciting challenges, we've known for quite a while that entanglement, is real, it's there. There was a recent Nobel Prize for the seminal experiments that showed entanglement between two particles. And I would say, to me, the most exciting research going on today is, in fact, about scaling. How many particles can we entangle? How can we have error correction protocols that allow you to, even if a little bit of information does leak away, to correct and to sort of preserve this entangled system of many? That depends now on the physical mechanism, but it's never going to happen faster than the speed of light. Here, maybe? Yeah.
Yeah, but she's.
She's.
We'll
okay.
get to you. We'll
Yeah.
get to you. Don't worry.
Okay.
When I read about quantum computing these days, I'm reading very little about the creation of new molecules. Does the creation of new molecules have potential to solve electron mass?
I didn't actually fully understand the last part of the question, but the question was about the creation of new molecules. And so I think there's a couple of different ways I can interpret this. So one is you might want to design molecules that have particular properties that are going to be useful in some drug, for example, right? And there you can ask, can quantum computers help us understand chemistry to the point where we can sort of engineer new designer molecules? And I think in terms of applications of quantum computers, we're still kind of at the very early stage of even doing simple, small proofs of principle of being able to predict something about a diatomic molecule with a quantum computer, but we hope that those proofs of principle will scale to the point where we can actually learn something useful for these sort of bigger problems about molecules that might be interesting, let's say for drug discovery. But I also want to add that there are people doing beautiful experiments building molecules in a very controlled way from single atoms. So I talked about the fact that you can trap a single atom at the focus of a laser beam, and there's work being done on basically taking two atoms and shining in a pulse of light that sort of converts those in a controlled way into a single molecule, taking arrays of these little molecules and controlling their interactions. And there's actually some really beautiful physics there as well, and doing controlled chemistry at the single molecule or two molecule level.
Thank you, Dr. Smith, for your presentation. This goes back to your point on decoherence, and one field that's experimentally quite notorious for being finicky is quantum computing and the problem of decoherence. And you've talked about error correction, but back to the hardware side, I know a lot of different companies are experimenting with just different frameworks to develop quantum computers, whether it's nitrogen vacancy centers, whether it's ion trapping. But are there any advances that you think we absolutely need to increase the number of total qubits that we can have in a computer?
Yeah, so I would say there's exactly which advance is needed depends a little bit on the platform. So for example, the sort of number of total qubits in these superconducting systems is kind of, I think, approaching kind of 100 superconducting qubits, and so that's already starting to be an exciting regime. There were beautiful quantum advantage experiments showing you can't classically calculate what these systems are doing. With the cold atoms I talked about, there are actually arrays of hundreds of qubits that are starting to be deployed as quantum processors, and so that's an exciting direction for scalability. The nice thing about, I'm a little bit maybe biased because this is a field I work in, but the nice thing about atoms is if I have let's say, rubidium atom, every rubidium atom is the same as every other rubidium atom, and so there's sort of this fundamental setting where one has identical particles and can scale them in a quite nice way. But in all of these things, one of the challenges is even just the kind of classical control. How do you assemble more and more particles into an ordered array, address each one with a laser beam that you can use to generate the quantum gates? But then also, how do you have kind of modular architectures where maybe, if I go back to the superconducting qubit platform, there's some number that will fit in a it has to be in a dilution refrigerator at low temperature. There's some number that will fit, and then how do you kind of connect that chip with some number of qubits onto another chip that has more qubits, the interconnect problem. You need to start to think about how to have architectures where you can have modules with some number and then start to scale and connect them to each other. And then the atomic or ionic qubits, those interconnects might be using light, actually, for example.
Hello. On a more philosophical note, do you have a personal favorite interpretation of quantum mechanics?
Yeah, that's a great question. I have to say that from my perspective, interpretations of quantum mechanics are a lot of fun to kind of discuss over wine and cheese or something. But in the lab, actually, you can calculate what's going to happen, and it works, right? So the theory works very well. But there are really great questions. I mean, one should be bothered by these questions of interpretation. So what's really, when I say we measure the system, and all of a sudden, the state collapses into the 0 or the 1, right? Why does the fact that I measured the system, why does that matter? What is that process of measurement? What's going on? Is it really a human observer coming in that matters? That shouldn't matter. So broadly speaking, I would say my understanding is when we do a measurement, it's actually I'm becoming entangled with that quantum system myself. And that becomes really hard to think about. There are fascinating interpretations like the many worlds interpretation, that there's different outcomes that, maybe they're all in some sense happening all of the outcomes are happening, and we just feel like we're in a particular universe where we saw a particular set of outcomes. But that to me doesn't quite solve the problem, because why do I feel like I'm in the universe I'm in and not in another one? And so I would say I love chatting about interpretations, but I'm not going to pick one.
So when you describe pinning an atom in place using lasers for quantum computing or research purposes, how much of a concern is the subsequent increase in uncertainty and velocity of the particle, and how do you deal with that?
So let me make sure I understood. So the question was, how much of a concern is the increase in uncertainty and velocity when I manipulate an atom with light, let's say?
Yeah, if you're pinning an atom in place, wouldn't it be?
Yeah.
Okay.
So it turns out that if I sort of bounce a photon off of an atom, there's a particular amount of energy it gets. It's called the so-called recoil energy coming from that photon bouncing off of it. which indeed translates into some uncertainty in velocity. And so actually, when one is cooling atoms down using light or trapping them, there's sort of this natural energy scale for how much uncertainty in the velocity is generated. And fundamentally, there's this trade-off where I really, quantum mechanics limits how precisely I can control the position and the velocity, right? And so that means that even when I talk about an atom being like pinned in place by light, it's in its lowest possible energy state. Nevertheless, there's some kind of probability distribution of where it might be and of how fast it's moving. And the point is that if we do a good job of all of our laser cooling, we can get to the fundamental limits of how small those two uncertainties in the position and the velocity are. And once you've gotten to those limits, then you really have quantum mechanically the atom in sort of the best defined state it can be in, and it's actually not a problem. But if if you're kind of sloppier and you're not, if you're a little bit sloppier, then you might have some finite kind of temperature of the atom. It's moving around more than the fundamental limits, and that motion can actually then pose a limitation to, let's say, how perfect the gates are in your quantum computer or whatever the application is that you're aiming for. Did that kind of answer the question? Yeah.
All right. Thank you so much for a fascinating conversation, Monika. Thank you.